Before we get started, a couple things. First of all, this entire research project was funded by the Joyce Foundation, so we'd like to take a second just to thank them for their funding, without which none of this research would have been possible. We learned a lot during the project. We found it was very interesting, and obviously we hope you do too. There's a full report that'll go into a lot more detail than what we're able to cover here in the next 40 minutes or so. So if you're interested, you are able to access that full report via the links page. During today's webinar, we're going to cover kind of three of these four main topics. The first is background, which is just kind of an overview of the research, why we think it's important, and what exactly it entails. Our study really goes into depth about what we did specifically, and then risks and opportunities. We'll talk really about the results that we found. In the second webinar, we'll kind of take those results and talk about how programs could use them in the future to capture more savings within the programs.
Yeah, so to give you a quick sense for what you're potentially going to get out of today, at least the first part of today's webinar, I want to jump ahead to what some of the conclusions will be at sort of a high level. Today we're going to talk a lot about energy efficiency programs, specifically programs that deal with whole building or comprehensive energy savings measures. So programs like new construction programs, deep or major retrofit programs. These types of programs are generally very flexible and technology neutral, but lately they've seen a significant risk in the eroding of their savings by increased stringency of codes. Specifically, the new energy code that's come out in the last year and this year is potentially going to have a negative impact on the savings from these types of whole building programs. But we, through conducting this research and in our day-to-day work on energy efficiency programs, see several opportunities where these programs can actually grow in savings and achieve additional potential. Some of those savings opportunities cover unregulated areas that are not regulated by code. Some cover the actual technical process that most of these programs go through. And some cover just an expanded scope. A few of those that we identified in this research include improving accuracy and completeness of calculations, going after unregulated building components that are not covered fully under the code, going after building energy usage that is impacted during construction, installation, and commissioning of the building, and then later during operation and occupant usage of the building. And then finally, potentially going after some energy impacts around areas of the code that people do not always fully comply with. So those are the types of opportunities that we'll be talking about today. And the first part of this webinar is going to be some background in how we studied a couple of buildings to determine what those opportunities look like. And then the second part of the webinar will be some recommendations surrounding programs and codes that build on what we learned in studying these buildings. So now to start, we want to go into the background of how we conducted this research. And really we looked at some actual buildings that our programs have touched in the past. And to frame those very generally, we came up with a framework of energy savings for a generic building. So this bar shows energy usage. Like I said, for a generic building, there's no units on the y-axis. The total height of this single bar plot is the energy usage of a generic building that does not give any thought to reducing energy usage. So a typical building that's built to minimum code, operated like typical buildings are, without any focus on energy savings. Just the blue portion of the bar, the much shorter portion of the bar, represents what the lowest achievable energy usage is using economically viable options. Of course, we have buildings today that get all the way to net zero. That is often not considered economically viable, even if you go through full life cycle cost analysis. But we can usually get quite a bit lower than the typical building is. The difference there is all represented in the green portion of the bar plot. And each of those green segments suggests that there's an opportunity for energy savings. Now you can see that in this framework, the typical whole building program, new construction or major retrofit program, is typically only going after a portion of that savings. In this case, the area that covers design improvements, and usually those types of programs are also able to cover some amount of the execution of the building components. And throughout this webinar, when we say execution, we're really referring to the contractor and other parties who are putting the building together, who are responsible for executing the energy efficiency improvements that the program recommends. So that would be in terms of execution, we're referring to installation, programming of controls, commissioning of the building, calibration of controls, and these types of things. And programs usually go after a piece of that too, but there are large pieces of that typical efficiency programs do not cover at all. Now we see there are opportunities outside of this typical scope. First, on the top, we see code noncompliance. Theoretically, not every building component that's out there in every building is built to meet code. This research will show, but our again day-to-day experience shows that typically buildings miss code in some areas. And then below the program savings section of this bar plot, we see a few other areas, including operations and maintenance and occupant behavior, that are not covered in any way by these programs. So this is just kind of a framework to understand the pieces of energy savings that we looked at in our research, with the hypothesis that if we are to begin looking at these other areas, we can probably show some economically achievable savings that we're not currently pursuing. And the goal of this research is to understand what those segments look like, and also do some rough quantification based on just a couple of buildings to show an order of magnitude for that savings potential.
Yeah. We kind of rank the different savings potentials such that programs could potentially spend their time developing programs in areas that would be most effective and bring the most savings into the program. Now just to talk a little bit more specifically about what we did in our study. Our methodology followed a pretty simple, straightforward 5-step process. The first step was to identify a list of buildings that have gone through our new construction efficiency programs that have been occupied for over a year, and so going through our program, there was a initial design iteration of modeling. One of our energy modelers came onto the design team, did a series of models in which they showed the energy impacts of energy efficiency upgrades, quantifying the energy savings, the incentives, and then a final version of the energy model was created that captured the total savings of the project for the final version of the design, and that savings was then attributable to the program. So once we identified a list of projects, we had to select only 2, unfortunately, to really study in more depth. We wanted to go really deep into each building. We wanted to really understand all the energy usages and impacts of the study, which takes a lot of time. And that's why we could only do 2. And go into that depth, we got past the normal assumptions that we usually make and wanted to really tease out what their impacts were. So that depth was required, and having only 2 buildings in our study means that we can't really extrapolate to a program-wide, but the results we show will definitely be orders of magnitude. Once we had our two buildings, we collected data associated with each one for use in calibrating our energy model. And what I mean by calibrating energy models, I mean the monthly natural gas and electricity consumption that the model predicts was updated until it matched the utility bills for what the building was actually using. Once we had this calibrated energy model, we could use it to study those areas of additional savings that Scott mentioned earlier.
Right, and I think it's worth saying that these two buildings that we're going to study here went through programs that that our team actually runs, but in looking at other programs across the country, our programs are run in a somewhat similar framework to other whole building new construction and major retrofit programs. So I think that we'll find the lessons we've learned are pretty applicable to other programs as well. Mm-hmm. So the two buildings that we were able to study were both of a similar type. They're community centers. The first one, Schuetter Community Education Center, it's here in Madison, Wisconsin. It's a smaller building, 11,000 square feet, small in terms of commercial buildings. It's a fairly straightforward steel frame construction, but generally a lot of thought was put into passive thermal and passive lighting measures in this building. So though the envelope is fairly simple technology, it was designed in a form that takes advantage of, again, passive thermal and lighting benefits. It used, again, fairly simple linear fluorescent lighting technology, but again, designed efficiently. And then for its HVAC system, it did use a high performance, fairly cutting edge technology at the time, ground source heat pump system with a dedicated outside air system. The second building, Plymouth Intergenerational Coalition, it's a little bit bigger building, included still a community center aspect, but also had, this building also had a daycare, which included a little bit more intensive kitchen operation, and then a senior center as well. This building was wood frame construction, a little more lightweight, and used a similar linear fluorescent lighting approach, and its HVAC system was more mainstream, a package variable air volume system. They did have a hot water system with efficient condensing boilers, whereas a lot of buildings this size may have just gone with electric reheat, so that was a good, efficient choice that they made there.
Yeah. In a sense, these buildings had a microcosm of the typical building types you'd see in new construction programs. They had kind of classroom or educational areas. They had office areas, kind of community gathering spaces, kitchens. They had a lot of different use types. So
that's good.
It is a little bit more extrapolatable than if we just got a straight office. The first thing we did once we selected the two buildings was to compare their energy usages, their actual energy usages, to typical or similar buildings in the area, in the region. And we did that by grabbing information from EIA's Commercial Building Energy Consumption Survey, or CBEX. It's a little difficult because in CBEX you can't just select the community center building type and it gives you the results. You have to, we took the building types I just mentioned, education, office, and area weighted averaged them to get the results that we showed here, because there's really nothing super typical about these. They're all operated differently. But with that said, we generated the information you see on the screen on the similar column shows the electricity, peak demand, natural gas usage, and energy utilization index for the similar building, and then the Schuetter Center, and then the Plymouth. And just kind of going down and comparing the results, you can see that first of all, the Schuetter Center and the Plymouth Center both have energy consumption that is below the similar building type. The peak electric demand is similar across all three buildings, and the natural gas usage is very different. The Schuetter Center has very low natural gas usage, and that's because of the ground source heat pumps that Scott mentioned earlier. They're not heating the building with natural gas like a typical building would, which makes their lower than average electric consumption all the more impressive. A different story plays out with Plymouth. At Plymouth, their natural gas consumption is actually a little higher than similar. And in that case, because we went to this benchmarking exercise, we knew that something may be a little remiss there. And when we were going further down the road, we were able to think, all right, let's check it out and just see if we can find anything that could be problematic in the building's operation. We then combined the electricity consumption and the natural gas consumption, which are in two different units, kWh and therms, and we put them all into one unit, which is British thermal units, or thousands of British thermal units. When you put that on a per square foot basis, that's your EUI of your building. A typical building has an EUI of 99, which is very similar for Plymouth, which also makes you wonder a little bit what's going on, because this building was designed to have energy performance goals to be under typical. The Lucier Center is roughly half of a typical building in terms of energy usage, so it's a very high-performing building, operated well. Yeah, and just to talk a little bit more about the EUI, again, it's one number that represents the entire building energy usage, and it's on a per square foot basis, so it really allows you to kind of talk between buildings, between building types, between building sizes, and that's how we're going to present our results from here on out in terms of one energy number. We then gathered a lot of information about each building. We started out going back over the design documents that we had from the original analysis, checking the as-builts, checking the specs, making sure that our model was in line with the design documentation. We then gathered utility bills for as many years as we could. Again, at least one is required, but I think we got up to 3 for the Lucier Center. That gives us the monthly natural gas and electric consumption that's going to come in so handy when we're doing our model calibration. And then we did walkthroughs of both buildings. So we spent time understanding the lighting, were the lighting counts accurate with respect, were the actual installed lighting accurate with respect to the plans? What were the plug-in equipment inventories? We checked HVAC nameplate information, as well as several other things. And during those walkthroughs, we also interviewed the building owner and maintenance staff, just to see, first of all, how they use the building. When are people there? When are people not? And if there are any issues associated with the energy consumption. Maybe a piece of equipment wasn't working, and they could tell us about that. We also interviewed members of the design team, mostly to see how they interacted with the program and if they had any suggestions for better interaction in the future. Apart from that, we got a lot of just recorded data from the building automation system, mostly with respect to the HVAC system, so flow rates, temperatures, set points, setbacks. And what we couldn't trend on a really fine interval data from the BIS system, we could get by putting data loggers into the building.
Yeah, primarily for lighting, which
Yeah.
the BS did not cover in either case.
Yeah, so we could get to see how the electric lights were operated, as well as if the controls were working optimally or not.
Right.
Once we had all this data, we used it to calibrate our energy model. And by that I mean, we started with our original analysis, which predicted energy usage and energy consumption of the building. And then we sequentially updated the software, put in actual weather year, and then updated all the different building components of the model until our predictions of energy usage from the model matched those of the actual utility bills. We followed ASHRAE Guideline 14, specifically the whole building calibration simulation approach, as kind of a sequential prescriptive way of doing calibration. We used the Train Trace 700 models that were originally created for the program, and the first step was the software update I mentioned. Now, Trace rolls out, Trace as well as many other energy modeling softwares, rolls out updates periodically, and each one is meant to create a more accurate energy modeling technique. So the algorithms within the energy modeling are just improved over time. And in that way, software developers are helping modeling accuracy outside of programs. We then switched out the typical meteorological year, which we usually use for the design level modeling, for the actual year that we are trying to match the utility bills to. And this had an effect on the energy usage of the models as well. We then sequentially updated the building components. So with envelope, for instance, we found that in actuality, the wall U values were 11% better than our original model showed. The roof values were a little better as well. was hard to find information about the windows, though. It's just difficult to get glass specifications. But we were able to really accurately calculate the installed interior lighting power, which for the Plymouth Intergenerational Coalition, we had to update from 1.1 watt a square foot to over 1.5 to capture its full energy usage. We also had to add exterior lighting, which wasn't originally included in the energy model. Now, if you want to match utility bills, if you want to match your model to utility bills, you have to include all the energy usages that are on the meter. So adding exterior lighting equally in the baseline and proposed, I might add, was a key step in getting the electric consumption to match better. We did some other updates with respect to the schedules, photosensor locations. For the internal loads category, our equipment counts from our walkthroughs were used, as well as our interviews to get the schedules more accurate. And then there's a lot of changes with respect to the HVAC. Fan power, supply air temps, flow rates, pump power, heating and cooling equipment efficiencies and capacities. And then we actually had to add domestic hot water in because it wasn't originally included in the scope of the analysis. After you go through this process, you go from an analysis which wasn't tied to the actual energy consumption to one that matches well. On the right, you see graphs of monthly electric consumption for one of the buildings, and in blue is the utility bill information. The electric consumption is pretty flat during the winter, spring, and fall, but peaks in the summer. You can see in green, at least the bottom portion of the green, the proposed model run. And you can see a large gap between the blue and the green. After a calibration process, the gap is very, very much minimized. Additionally, the area of the green, which is the energy savings, has changed as well. And we'll talk about the magnitude of that change as we get into the results section of the webinar. Now that we have calibrated energy models for both of our buildings, we study them and try to check out areas of additional savings that we could capture. Those areas fall into kind of three different groups. There's scenarios, sensitivities, and code impacts. Scenarios are areas within the traditional scope of new construction programs, but that aren't always captured by new construction programs. The expanded scope category is meant to kind of analyze a scenario under which the modeler has plenty of time and is not constrained by time or budget to understand all the energy impacts of the actual design, like the exterior lighting and domestic hot water that we mentioned previously. The best practice scenario is meant to study what additional savings could have been obtained by the buildings had the design team and owner had unlimited, I guess not unlimited budget, but a substantial budget to go after the economically viable technologies that are available. So more efficient equipment, more efficient lighting. And in that sense, we used Advanced Buildings Core Performance Guide for guidance, as well as just our own experience from designing buildings. In that scenario, we looked at more roof and wall insulation, better windows, better lighting, daylighting controls, ERVs, energy recovery, demand control ventilation. So a lot of different things that the buildings could have done had they had more time or more budget to explore. The sensitivities are actually fundamentally different than the scenarios. By that I mean, within the scenarios, we had, for our baseline, the code to read for our inputs. So there was a table in the code for what are the U values of the windows and walls. And for our proposed case, there was mechanical schedules, or the information we grabbed from our visits to the building. So the inputs to the models were really well defined in the scenarios. With the sensitivity, that's just not the case. And it'll become apparent in a second, but the difference is not a baseline and proposed in the sensitivities. It's a lower performance case versus a higher performance case. Those sensitivities fall into four categories. Unregulated, those are unregulated components of design. There's execution, which is about quality installation and commissioning. Operation, which is about preventative maintenance and cleaning. And occupant behavior, which is just responsibly using the building. To give you kind of an idea what a typical sensitivity looks like, think about under the operational sensitivity a scenario in which the building maintenance staff has been both educated and motivated to save energy. If you compare that to one that isn't, you can imagine the difference being that the one that is very motivated would clean the filters, regularly maintain the equipment, and in that case, there's energy savings to be had. But how do you model that? And for us, we modeled an additional fan power of 0.2 inches per, inches of static pressure, and a 5% degradation in the heating and cooling equipment. And again, those don't come from any schedules. There's no tables that we can go to reference that, only kind of our engineering intuition and some data sources that we
there's some
find.
secondary research on some of those items, but they're not in any way regulated.
Yeah, which is kind of the point. These are areas of savings that are out there, and we need more research around them to help generate these numbers. And then finally, we looked at code impacts. So how does the increasingly stringent code impact the energy usage of the building, specifically the energy baseline, and therefore the savings? So we've talked about our process, and we've given you some background about the research that we did. And now we can get to the results. So what did we find? Starting with the kind of the accuracy of the predicted savings. So we're talking about how our savings originally compared to the savings after we went through the full calibration process. You'll see graphs shortly that show energy usage and energy usage savings in terms of the EUI that I referenced previously. And that can really be thought of as, I've heard this analogy a couple times, like a miles per gallon for a car. Except for, instead of with cars, the higher the mile per gallon, the better. With EUI, it's the lower, the better. Again, it's on a kBTU per square foot basis, and 100 is typical. So whenever we reference like numbers from now on, if we say kBTU savings of 20, it's almost like we're saying percent savings as well, which is kind of a useful coincidence. Yeah. And this graph needs a little explanation because it's kind of busy. And by that, and it's going to be shown in a few different variations for the rest of the webinar. It shows EUI plotted on the y-axis versus a variety of scenarios or sensitivities or steps on the x-axis. In the blue area, the total blue area, is the actual predicted, the proposed predicted energy usage of the model. The lighter blue section being the gas usage and the darker blue section being the electricity usage. Sitting on top of that is the savings at each step of the calibration effort, with, again, a light and a dark component representing the electric and gas savings. As we step sequentially from left to right, you can see how the model predictions in terms of savings and actual usage change as we go from the original analysis to the updated software, which actually changed it non-negligibly. It was one of the biggest drivers of a difference in savings. To the actual meteorological year, or AMY weather file, and then the building components, envelope, lighting, internal loads, and HVAC, until we get to our calibrated energy model on the right. We start off with a model prediction of 63, of an EUI of 63, and we end with a much higher model prediction of an EUI of 98, which matches well, if you look at the bottom, the actual measured EUI of 96, which came from the utility bills. So we achieved model calibration, but our model has changed its predictions drastically, most of which came from that natural gas usage that we saw. Again, this is the Plymouth Intergenerational Center, I should mention. The majority of the increase comes from the natural gas usage that we saw in our benchmarking, which occurred due to simultaneous heating and cooling. There was an in-floor radiant system that was keeping the floor very comfortably warm while the HVAC system was cooling the space. Mm-hmm. So that's why the major cause of the discrepancy there. We also see that throughout the calibration process, the energy savings actually decreases by 9 EUI. This is a 22% decrease in the energy savings that the new construction program originally claimed, but in actuality was happening.
So though the order of magnitude energy usage changed by 50% or so, the savings that does not reflect that big of a change in the percent savings. So our percent savings calculation is still reasonably accurate.
Yeah. A much different story is shown with the Lucier Center. The same progression from left to right as of our calibration process. And we start out with a predicted EUI from our original analysis at 46. We end with 46. And the actual measured EUI of the building from the utility bills was 46.
Yep.
So the modeler hit the energy usage of this building dead on, although I should note that the very end of the process there was a little bit of natural gas usage added to the building to account for a unit heater and the domestic hot water. However, the electricity consumption was coincidentally reduced in that last step of the HVAC step to make the beginning and ending bookmarks of energy usage remain the same. Right. Throughout this process, the energy savings of the building actually increased, though. It went the opposite way of the Plymouth Center. For the Lucier Center, it went up by about 15 EUI. Taken together, you could kind of think that the calibration effort leads to a little increase in savings. Maybe it's a wash. With 2 billions, it's a little hard to tell, but generally, it increases this amount of savings.
Yes.
And that's the calibration effort. Now we're going to get into the scenarios, the expanded scope and the best practice scenarios.
Right. Thanks, Scott. So, the calibration exercise was very interesting. We learned a few things. Again, the fact that one building went up, one building went down is understandable, and that's not really the key result that we were shooting for anyway. What we're trying to do now is look at order of magnitude impacts from these different perturbations of the model. So in this plot, we're going to show the two scenarios that Scott described earlier. On the plot, the first two bars you've already seen. One's the original analysis. The bar on the farthest left is the original analysis. The second bar is the analysis with the calibrated model. Those are just shown for reference here. First, we look at expanded scope. So now what if we were able to expand the scope of our analysis to all the building components that were installed, and not just those which the design team and the program decided to look at under the scope of the program. And we see that if we're more expansive with that scope, we see an increase in energy savings. In this case of 10 kBTU per square foot. So you see the proposed didn't change. All we did was really increase the baseline energy usage to account for additional scope that the program could cover. The final bar on the far right is for best practice. And again, this is if the owner was able to incorporate everything that was economically viable, usually due to budgetary reasons, timing, and just our ability to coordinate everything into the perfect design. We never quite hit the economic optimum. In this case, we would have seen an additional savings of 17 kBT per square foot if we would have achieved best practice. In this case, we were looking at additional savings from adding in energy recovery, demand control ventilation, so some HVAC measures covered the majority of that savings increase. We were not able to get those into the more basic HVAC system that was actually put into the building. Thanks, Scott. Oh, and you'll notice the best practice scenario has the opposite effect on the results. The overall baseline, we kept the same. The proposed decrease because we put more measures into the building. We see very similar impacts with the Lucier Center. If we're able to expand the scope of the program's influence, we can gain an additional 9, roughly, kBTU. And if we're able to push the owner to achieve best practice, we see an additional 7 kBTU. Yeah. So all those things are on a similar order of magnitude, sort of 10 kBTU, for just expanding our scope and just being more comprehensive. And an additional 10 if we're able to push them on the measures that we already covered, push them a little further.
Yeah. Yeah, so that was the scenarios, and now we can talk a little bit more about the sensitivities. Again, this is comparing a lower performance case to a higher performance case. And for the unregulated sensitivity, this table, obviously a little busy and we don't expect you to read everything.
Mm-hmm.
If you're very interested in what we did specifically, that's all in the report.
Mm-hmm.
But I just want to highlight a few things that we looked at in the unregulated sensitivity. The first, under the architecture component, is the glazing placement and size. So the glazing is optimally configured, and the window area is not, maximized, but rather optimized to let in enough light without letting enough heat out, or too much heat out. Under the internal loads, we looked at kitchen equipment. Specifically, the exhaust is the kind of the major driver with respect to energy usage in the kitchen, and we looked at variable speed exhaust hoods, optimally placing the hoods to minimize the amount of exhaust they need, all of which had an effect on the energy usage of the buildings. And then in the HVAC category, the codes say what amount of ventilation air you have to provide at a minimum, but they say nothing about the maximum. And as you increase ventilation rates, there's definitely an improvement of occupant comfort. But there's some point at which you're just bringing in a lot of outside air without improving it and using a lot of energy accordingly.
Yeah. And the code doesn't prevent you from just doubling your ventilation rate if you decide that's what you'd like for the building.
So what would happen if the ventilation rates were lowered to code minimum? And then we also looked at 2 system switches, one for each building. And by that I mean HVAC systems, specifically for the Plymouth Center, were switched from a hot water to an electric reheat, and for the Lucier Center, from rooftop units to the ground source heat pumps.
Because system type is not regulated either.
Yeah.
You're free to choose whatever system type you would like for your building.
As soon as you do, then you have to meet some minimum level of efficiency, but you can choose any kind of system type to provide that heating and cooling.
Yeah.
So again, you see the kind of the progression from left to right within the sensitivity in terms of the architectural, then the internal loads, HVAC, and the system switch. And you can see that the architectural had a little bit of an impact. The glazing placement information we mentioned a second ago. The internal loads had a greater impact, and the HVAC system had a much larger impact.
Mm-hmm.
The system switch was kind of a weird one because it's really about fuel switching from electric to natural gas, and not about a more efficient HVAC system as a whole.
Yeah. So that bar's a little misleading.
Yeah.
It would be higher in some buildings with some system switches.
Yeah, true. And that's actually played out dramatically for the Lucier Center. The architectural and internal loads components didn't have that big of an impact, but the HVAC did. And again, that's the ventilation, properly designing the bore fields, the pumps as well. But then the biggest amount of savings came when you made the switch from the kind of standard rooftop units to the high-performing ground source heat pumps.
So now we go beyond the sort of usual scope of programs, which is the design phase, and we go on to the later phases of a building. First, with execution, we look at things like infiltration reduction. So how well is the envelope actually put together? That's not usually handled under a whole building program, but it absolutely has an impact on energy usage, of course. How well the lighting controls are actually implemented, how well the VAV system is programmed, balanced, and otherwise controlled. Usually there is some ability during the design phase to set up a sequence of controls, and the better that's done, usually the more effective the controls will be in the space. But there's a huge amount of impact from bad versus good execution of those controls and balancing and so forth. And all those things have a pretty significant impact on the building. Similarly with, as Scott mentioned, ground loop implementation. You can have a really high quality installation of a geothermal bore field and one that's not quite at that level. And that'll make a big impact on energy savings. That usually doesn't come into play in these programs. Similarly with implementation of demand control ventilation.
Yeah. And we'll get into the results of these last sensitivities at the end after we kind of talk about them each individually. For the operational sensitivity, again, we're talking about maintenance, cleaning of the building and its equipment. In the HVAC system, the major driver was just keeping the filters and coils clean periodically and making sure that any systems that have the potential for simultaneously heating and cooling are not doing so. And then kind of standard maintenance of your heating and cooling equipment.
And then finally, we look at occupant behavior. Again, something that occurs well after design, but there's potential for some energy savings there. We found that the big impacts were in areas where you had significant energy-using equipment, so like kitchen equipment or photocopying equipment or process loads, and not just computers and monitors and TV screens. There's much less impact from occupants in those cases. So the kitchen was a big area of impact. And then whoever has control over the overall thermostat set points also has a large part to play. So in terms of occupant behavior, it may be more about influencing the behavior of a very small number of individuals in the building.
Yeah, the key ones. And then this is the result. This is the coup de grace, the results of all of our analysis.
Yeah, if you're going to take away one slide in your mind, this might be it.
Yeah. Shows for each of our scenarios and our sensitivities the EUI savings, the kind of the high and the low end. The major one being that unregulated system switch from a low-performing rooftop unit or PTAC unit to a high-performing ground source heat pump unit.
Yeah, or going from electric heating to some other form of heating.
Yep. The unregulated components of design, so specifically like ventilation rates being at their minimums, and I'm blanking on a couple
window
of
placement.
Yeah, window placement had the next largest amount of energy savings potential. And then the two scenarios and two of the remaining sensitivities kind of had a very even impact. The expanded scope and best practice, execution and operational sensitivities were all very similar, like 12 to 13 EUI of savings. And then occupant behavior was the lowest on the tail end, about 8 or 9 EUI of savings for occupant behavior programs.
And before you move on, it's worth mentioning again that the savings that the programs demonstrated in these buildings was on the order of 30 kBTU per square foot, or on that order, and all of these potentially could add substantially to that. Most of them are in the range of 10 to 20 kBTU of additional savings opportunity.
Yeah. That's a great way to kind of couch the savings. 10, 20 may not mean much, but when you compare it to the actual savings, it starts to come into a little perspective about how much potential there is out there.
Yeah.
Now that we talked about potential, we can go the other way and talk about risks. And our whole kind of premise is that there's a lot of risk out there with these programs. They have to meet their goals, and the codes just keep getting stringent. So how are they going to do that? We talked about ways that they can offset it, but now we're going to try to get a little bit of an understanding around just what the magnitude of decreased savings would be. Before we get to that, though, we found some areas of noncompliance. Specifically, in going through the buildings kind of with a fine-tooth comb, we found that several of the wall and roof construction insulation values were too low. In one of the buildings, the installed interior lighting was much higher than the code-required minimum or maximum, and an economizer was not present in one of the required units. In talking to the design team, anecdotally, one of the lighting designers says that they had never been asked to provide compliance documentation about their lighting design. And another design team member said that the program actually helped them understand the code and how to comply best with it. We'll talk a little bit more about both of those in the second webinar. But to kind of wrap up our results section, we modeled the difference between the code baseline that when these buildings actually went through design, which was ASHRAE 90.1 2004, and then we compared what the baseline would be under a 90.1 2010 baseline. There's differences with respect to all the envelope properties, the lighting. Lighting controls were sometimes mandated in certain areas. Efficiencies, fan powers, demand control ventilation was required in certain areas where it wasn't originally. And taken together, that decreased the baseline and therefore the savings on the Plymouth Center by almost 27 EUI, which is essentially negating the majority of their savings. Their proposed building is very much in line with the stringent code at this point. At the Schuetter Center, however, the savings wasn't reduced nearly as much. In fact, it only goes down by 10. There's still a lot of savings there, which is really getting to the fact that the Schuetter Center is a high-performing building, still performing well, even relative to a more stringent baseline. So taken together, kind of 10 and I forget the other one, but the stringent code was, on average, kind of a reduction in savings of like 19 or 20, which means that you kind of have to go after programs in a couple of the areas that we talked about previously in order to kind of make up for that loss.
Yeah, that's a good way to think about it. So to conclude, and we're going to cover this more in part 2 of the webinar, we have a series of recommendations that come out of just looking at 2 buildings in detail. And those are program policy type recommendations. And they all lead to opportunities for more savings. We're talking about improving the scope and completeness of calculations, addressing unregulated components and HVAC system types, incorporating some amount of quality control in the execution or installation, then looking at O&M and behavior, sort of after the building's constructed, and then finally looking at actual code compliance. And if you're to summarize this into sort of 2 main takeaways or adjustments you could make to program design, they would be to try to expand your baseline and cover more ground than programs are currently covering, and then to try to expand influence later in the building's life to the actual installation of some of these measures, for example, and beyond. We have some additional resources here. We're almost out of time, so I want to at least leave a chance for one question maybe, so I'm not going to go through each of these, but most of the information that we referenced from secondary research to do what we did is found in these references.
Which are all in the links portion of the
correct
the tool,
so
the media site tool.
Yeah, just go ahead and head to the link section for those.
And I think that's it. Time for final reminders from Andrea.
We have a question about, a viewer wonders if you looked at possible interactivity of EUI savings potential.
Yeah, definitely. Through our whole building analysis, our modeling, every ECM is interactive, meaning that when we decreased the lighting power, the HVAC responded accordingly. And that's kind of the power of a whole building energy model, is that it is very interactive in nature. When we went through our progressions, they were additive from left to right, so the changes that occurred in the previous step were captured in the next step as well.
Right. Though for the sensitivities, those were not additive, correct? So you could not necessarily capture, you could not just add up all the KB2 savings from the sensitivities and assume that you can get all of that. They are going to play off of each other and eat into each other's savings a little bit.
Within any given sensitivity, like the architectural, lighting, and HVAC components,
right,
those are additive. But then as soon as you start comparing between sensitivities, you're right. You couldn't capture 40 and 20 and 12 and 12 and 12. That would be all the energy usage of the building plus.
Right. So with it, to maybe summarize it, within each of the bullets on this plot, each of the points on this plot, we did account for interaction in all the measures we stacked up. But you could not take each of these points and stack them on top of each other.
Yeah. Hello, welcome back. Thanks for coming back or joining us for the first time if you missed the first webinar. Again, this is the second part of our 2-part webinar entitled Midwest's Energy Codes and Policy, Reaching the Full Potential this time. I will try to moderate this round in place of Andrea and hopefully do her justice. The second webinar entitled Manufacturing Jobs and the Policy Conversation. I'd like to introduce two new panelists. First, Marge Anderson, the Executive Vice President of the Energy Center. Marge is passionate about building the human capacity to generate economic and environmental sustainability. Her work addresses technical and human behavior knowledge gaps that prevent sustainable energy use in buildings. Welcome, Marge.
Thanks, Scott.
And then you will meet Joe Kramer shortly. He is a senior project manager at the Energy Center. His skills as an economist and environmental policy specialist serve him well in quantifying and analyzing the Midwest's energy resources. So when he comes on, thank you, Joe. Before we begin the content of the webinar, I want to take a moment to again thank the Joyce Foundation. They funded this research, and without their support, it never would have been possible. So thank you, Joyce. We definitely found the research interesting, and hope that you do as well. During today's webinar, we'll talk a little bit about framing the research, why it's important, just some background around it. We'll then go into program considerations or recommendations that came out of Scott and Mai's research that we presented in the first webinar. And then we'll talk a little bit about connecting utility programs with manufacturers.
I wanted to give a little bit of context about why we looked at these two projects funded by the Joyce Foundation. At the Energy Center, a big hallway conversation here is about how come after decades of energy efficiency programs and an increasingly evolving building code environment, we're still leaving energy savings on the table, and we know that when we do work in this industry. So how do we accelerate energy efficiency? How do we pursue deeper savings? And we are thinking here that one way is through a more aggressive energy efficiency policy. And do policymakers need some different frames and some different lenses to take a look at those issues? So we wanted to look at a couple of frames. One, we wanted to look at what was happening in real buildings with codes and standards, and one with economic development and energy efficiency. So this webinar will show the results from two research projects, and we have our experts with us today. In the first one, which is a follow-on from the technical webinar that preceded this one, we know that codes are raising the bar for compliance for energy efficiency programs. We wanted to see what would happen to the savings in a building once we had a year of real performance data and get that real world data, see what savings were left behind by policy and what kind of opportunities and advice could we offer to program managers and evaluators for them to consider. And Scott Schuetter and Scott Hackel are going to share that research with us, the recommendations from that research. And the second part of the webinar, we're going to take a look at the economic opportunities. There's been so much conversation in our industry around job creation and energy efficiency, but almost all of the conversation that we've seen, including what we looked at through a pretty extensive literature review, addresses the jobs created by people actually installing energy efficiency measures, trade allies, contractors, installers, and people like ourselves who implement energy efficiency programs. We couldn't find very much existing data on whether there was a link between manufacturing jobs and energy efficiency. And here in the Great Lakes, where we have a recovering economy and a strong manufacturing opportunity, we wanted to see if there was a better connection that could be made. If there is that connection, that gives our policymakers an opportunity to think differently about the benefits of energy efficiency and the importance of aggressive energy efficiency policy for our region. And so Joe Kramer is going to be here to share the results of his work. So first I'd like to give the microphone back to my colleagues Scott and Scott so we can hear from the technical perspective on the ground with some real buildings. What recommendations do they have for program managers, policy makers from their analysis?
As Marge said, we want to discuss program policy, program design, and how it can broaden and increase savings even in the face of the more stringent energy codes that are often seen these days, especially this year, as maybe a more primary driver of energy savings. We found in the research that we conducted on two specific buildings that had gone through energy efficiency programs, that was what we covered in the previous part of the webinar, if you saw that, was that there are additional opportunities that we can go after for more savings with these programs. It's potentially going to require an adjustment in not just the way the programs are run, but maybe even in the policy framework, the constraints around the program, in the evaluation framework around these types of programs. More specifically, we lay out from the results of our research 6 recommendations for programs. And the first one suggests improving the accuracy and completeness of the calculations within the program. So that suggests improving the way the programs are run. The next 4 kind of cover rescoping or reframing what these programs are going after, looking at some unregulated components, looking at the actual building operation and execution. And we'll go into each one of these in more detail in just a second. And then finally, we look at how programs interact. We looked at how programs interact with the energy codes and found that, yes, the new energy codes are going to result in substantial energy savings, which means less savings for programs. But there's still some opportunity there for programs. Now we'll go into each one of these in a little bit more detail. First, in looking at the accuracy and completeness of calculations, we showed in part 1 of this webinar that the accuracy of program calculations is generally fairly high and doesn't have a big impact on savings differential. There's not a lot of opportunity or risk there. We did determine that you want to be careful about software limitations. The key maybe inaccuracy we found is some software is not modeling certain system components correctly, but it was generally a minor issue. More importantly is the second bullet, that the analysis in most program processes can be broadened. And there's 2 sort of main ways we look at that being broadened. First, when we calibrated our analysis from our program analysis to the actual building operation, we found that there were all these components of the building that were not operating according to design, and therefore not really operating according to the model. That's not to say that the energy improvements that were suggested by the program were not implemented right. It's more just a general phenomenon of building operations. Equipment never quite operates optimally. This plot shows just one example of many. This is a plot of the speed of a variable speed pump in one of the buildings. According to design and according to control sequence, this pump should modulate down to 30% speed at the lowest loads of the building. And we see here in this plot, over a year of operation, it never comes close to 30% speed. In fact, for most of the year, it's up above 60%. And we saw this with not just this pump, but with VAV system operation and modulation, fan speed, and other areas of, economizer operation and other areas of HVAC operation. So this just suggests that perhaps we need to, in our analysis, consider the imperfect operation of the building in all cases, which actually should create more energy potential for us to go after in saving. The second area we saw analysis could be broadened is simply including estimates for energy savings where our current tools don't allow us to do a robust calculation. So there are limitations to the tools that we use for energy calculation, but if we have a recommendation to make and it can't be covered by the tool, maybe we should make an estimate and just make the recommendation anyway. The second recommendation area is in unregulated components. So there are a whole host of areas that are not regulated by code. Here I'm talking about code baseline. That in program speak, we usually call that a regulated component is covered by the code baseline. There are areas that are not covered by that baseline. Glazing placement in architecture. In terms of internal loads, the amount of plug load equipment, the design of the kitchen hoods and the layout of the equipment. In HVAC, the zoning of the building, the ventilation rates that are used. None of these things are covered by code and are not often baselined in programs. So there's an area for additional savings. Similarly, as we mentioned again in part 1, the biggest impact we saw was from the selection of the HVAC system type for the building, and that's not regulated by code either. Whether you choose a geothermal system or a basic rooftop unit system, the code doesn't tell you. So we're here suggesting one possibility is take sort of a three-tiered approach to actually have a baseline in your program for HVAC system type, and that can lead towards capturing savings on every project from HVAC system type. When the program gets involved, you can determine how to choose the baseline. If when the program gets involved there is no system at all selected or designed, we suggest that the baseline is simply the typical system for that region. Now, a lot of, or some people point towards 90.1 Appendix G as a potential baseline, but Appendix G ignores climate, it ignores building type, it ignores all these things, and it's fairly rigid and simplistic. Programs actually are operating in a given territory with a given set of design teams usually, and a given typical installation. So that's what should be used as the baseline in that region. What is typical? Usually you've got a few dozen previous buildings of that type that you can use as your baseline. If the program gets involved in a project and there are already multiple options on the table for HVAC systems, or maybe there's one option but there's the potential that it could be value engineered out, then the worst possible option is the baseline. And finally, if the program gets involved and the HVAC system's already chosen, it's very clear that's the direction they're going, then that system actually should be the baseline, and you can simply use the code minimum component efficiencies to build up that system type. So we suggest that even though system type is not a rigid piece of the code, that programs have all the capacity they need to make it so within a program.
Yeah, particularly if the program is involved very early in design. If they're early in design, then they can really influence the big drivers in energy, which we saw from the last webinar, one of which is HVAC system type.
Right. The later you are, the later you come into the project, the less scope you have in terms of system type, system selection.
Yep, there's just less room for changes to be made within the design. So that covered the first sensitivity. The next is the execution sensitivity. And there we found that, again, we're dealing with quality installation, control programming, startup, calibration, commissioning. And that's commissioning of building components at the time of installation. We found substantial savings opportunity in the first webinar. And basically, they could be used to require things like quality installation of air barriers, balancing of VAV systems, programming of lighting and HVAC controls. And that would not only ensure the savings that the program initially predicted, but also provide a few opportunities for additional savings on top of that. Execution programs could be implemented by requiring commissioning in order to receive the incentive, the initial incentive. It could incentivize commissioning directly by incentivizing a portion of the commissioning agent's fee. A program could also develop guidelines for specifying optimal equipment operating parameters or additional support for designing controls. A couple of our design team, during our design team interviews, recommended that programs just provide more information about the best way to control or commission a system. And then moving on to the operation and behavioral sensitivities. We found that there's a lot of savings to be had by ensuring commissioning and proper installation, as well as good operation of the building once it's occupied. And that kind of suggests a bimodal approach with respect to programs. They need to spend a lot of time early in design to get those big energy decisions and drivers correct, system type, orientation, massing. And then they tend to walk away from the building once the design is complete or the building construction is done. But programs could really influence at the time of installation of building components, their commissioning, and then after occupancy, how the building is maintained and operated. So there's an additional component of time that programs could spend on a given project and realize this additional savings. They can do, in terms of the operation and behavior, there's kind of two ways that programs could be developed. One is training, under which you could require a certain amount of training for building maintenance staff, or require a maintenance plan be in place in order to achieve incentives. A program could also provide that training directly surrounding key technologies that save a lot of energy, or develop guideline and materials for maintenance best practices. Finally, they could incentivize creating and executing a maintenance contract. And then we found that occupant behavior didn't have as big of an opportunity for additional savings, but what there was there would be best gone after by programs by focusing on the key energy decision makers in a building: kitchen maintenance staff, data center operators.
Whoever's got control over the thermostats.
Training them, and then they can have big swings in terms of energy savings as opposed to trying to get everybody to turn off their computers when they leave. And then we talked a little bit about the code baseline and how savings will definitely decrease with this more stringent codes. Point out that code noncompliance exists, but that it exists under a much less stringent building code. And as the codes become more complex and more stringent, the few instances of noncompliance that we found will likely only increase as the code is just harder to understand. And programs could help to improve compliance by educating design teams on how to meet code. It could also do so with training, although training is kind of hard to claim savings from. It's just a little more fuzzy of an area for savings opportunities. Generally, there's more research to be done in terms of how much additional savings is out there in terms of noncompliance.
Yeah, but it seems like it'd be easier for a program to go after, to prove up savings by showing that noncompliance typically in their territory, as opposed to trying to create some deemed savings based on training or something like that.
Yep. And then just to wrap up, there's kind of two areas that we recommend programs go after in terms of additional savings opportunities. One is just expanding the scope of their current program to include things like HVAC system switches, proper zoning, minimum ventilation rates. And the other is really influencing not the design, which is bullet one, but the installation and operation of the building, kind of at the tail end of construction and the beginning of occupancy.
I know there's a lot of work being done nationally to pursue outcome-based codes, and I'm interested in what differences you would have seen in your research or in your recommendations for program managers if we had outcome-based codes now.
I guess the first thing I'd say is that outcome-based codes are kind of the way to ensure energy savings. If you go and you measure the energy usage, then you know that the energy savings is occurring. It's often very difficult to take that extra step because of just the time involved. And if the project budget is such that you've already spent most of it with modeling and design, then it's hard to get to that next step. But with that said, there are definitely opportunities. I mentioned the simultaneous heating and cooling in one of our buildings. That would have been caught by a program that went in and measured the actual energy usage and looked for opportunities for additional savings. What I would mention is that the model could be used to find those opportunities without going in and really searching through utility bills, which are often hard to, without a model, to know whether the energy usage is high or not, because, for instance, our two buildings were not very much like typical building stock. So what is typical for that? It takes a lot of time to understand that, and there's a lot of error in that comparison as well.
Yeah, so that points towards the reason why outcome-based codes may not fit all buildings, and we may still need a lot of this type of program. It'd be very hard to create a benchmark for a building like the Plymouth Intergenerational Center, which has a daycare, a senior center. But to Scott's other point, I think you will need some type of program like this, and maybe it's not run by utility, I'm not sure how it works, but to show the design team along the way that they are going to meet the code. And maybe you can get the owner to pay for that, but that remains to be seen and tested.
I'm going to pick up all my mics and slide over and welcome Joe Kramer. We probably better test his mic so he can let you know what he found out in his research about connecting energy efficiency and manufacturing companies.
Okay.
Great.
All right. Well, figure out how to move this forward. The goal of this study was to improve our understanding of how utility efficiency programs contribute to regional economies. And in this case, we're focusing on the Great Lakes region. The focus of our study is looking at manufacturers of equipment and materials that are used in the utility efficiency programs. We didn't cover other aspects or other important players in these programs, program administrators, trade allies, and wholesalers and suppliers, all of which are important components and play a role in that. But our focus here is on the manufacturers of equipment. So the concept for this study is pretty straightforward. We look at a utility program, trace the chain of service providers to the products that are used in the program, find out where those products are made. The important thing is that we're actually tracing that connection. So we're able to connect program A with product B, which is made in these locations. The methodology that we set out to do this was to work with utility program administrators. Through them, get a list of active contractors, some subset working with that particular program, work through the other parts of that supply chain, trade allies, wholesalers, factory reps, try to figure out or get down to the point of finding where the equipment and materials are being manufactured that are being used in that program. This didn't work for most of the cases we were looking at, largely due to program administrators not feeling compelled to participate with us and share information. And that kind of forced us to reevaluate our scope and limited some of the data that we could get. And we ended up relying on more of an opportunistic methodology where we're taking information where we can get it. The programs we looked at were all related to commercial retrofits. And we looked at, in two different states, in Illinois we looked at ComEd, NICOR, Peoples and North Shore Gases programs, and then in Michigan it was Consumers Energy and DTE Energy. And this slide is just to give you kind of a perspective on where we drew our information to help you better interpret the numbers that we come up with. So if we start out looking at all the efficiency programs in Illinois and Michigan utilities, we narrowed it down, looking only at selected utilities, as I outlined on the previous slide. Within those utilities, we looked at commercial retrofit programs only, and then within those programs, we looked only at lighting, building shell, and HVAC measures. We were able to get the contact information on only a small subset of allies working with those programs who we contacted, and some of that group responded, giving us names of some of their suppliers. So our list that we eventually generated was based on that list of suppliers we were able to get from trade allies. So needless to say, the list represents an unknown proportion of the actual manufacturers connected with these programs. It's not in any way presented as a comprehensive listing. So given this small piece of the pie, what did we find? We were able to identify 46 different manufacturing locations providing, in the Great Lakes region, providing materials or products for the programs we looked at. And again, we know this isn't a comprehensive list. In fact, there are probably people on the webinar who could point out spots on the map that should be on there. But given the sources we worked with, these are the ones we were able to identify as positively reporting or working through these programs. And the composition of these plants was 28 of them were advanced lighting systems or components manufacturers, 16 made HVAC systems or controls, and there were 2 that were making insulation products. So what did we learn from this exercise? We found that these utility programs support manufacturing jobs throughout the Great Lakes region and beyond. We actually identified 85 manufacturing locations, if we look beyond the Great Lakes region, that are directly connected to those programs. Manufacturing sector, again, is just a fraction of the economic, represents a fraction of the economic benefit from those programs. And the other parts of the supply chain are also benefiting as well. And the Michigan utilities actually have incentives promoting purchase of in-state manufactured products that likely magnify the benefits for the state of Michigan, like the Buy Michigan program. And finally, it's really important to work with the utility from the outset in a project like this, and their participation is really necessary to get access to program activity information. What are the next steps? It's really important that we quantify these economic effects. And to do that, need information on qualified projects from the utilities, and product and volume information for manufacturers supplying materials to these programs is also really important to help give perspective on the level of influence that demand generated from these utility programs has. And ultimately what we want to do is an input-output analysis of the energy efficiency industry. We can do that using actual program activity data, provides a very solid analysis, and can come up with good numbers for how these programs affect state and regional economies, and produce estimates of things like job numbers and economic activity. That's the end of my portion.
Great. Thanks, Joe. I do have one question for you. It looks like there is a direct connection, and there's a lot more work that could be done to really talk about what kind of jobs are available as a result of advanced energy efficiency programs. What were the hot spots that you saw for the Great Lakes region? What kind of products could we tie more carefully to policy?
Well, it seems like there's a real proliferation of lighting, high-tech lighting companies, and but from the numbers that we had and the limitations of this study, it's really hard to make a judgment on that.
Right.
The Great Lakes region has always been strong in manufacturing, so really any of those areas seem like they could be good potential hotspots.
Great. So more work to be done.
If you have any additional questions, we would love to address them offline. Please use the chat balloon to do so and include your email address when you do. Please share any feedback you have with respect to the poll questions or just feedback in general by using the chain links icon at the bottom of your screen. You can watch anytime by using the same link that you used to access this webinar. You can download the full study at this link, as well as contact us directly. So, thanks for joining us. Thank you again to Joyce for funding the research, and have a great rest of your day.